Today we're going to quickly go over how to produce a sampling distribution and how to calculate standard error in R. The first thing we need to do is come up with some sort of data set. So let's say we want to use the iris data set. So data iris. And we are actually just going to use sepal length. So SL. And if we take a look at SL, there are 150 observations. You can also take a look at a histogram of SL and take a look at the distribution of these samples. Now, what we can do is we can assume that this iris sepal length data is, instead of being a sample, is the entire population, which of course is not true, but for now let's just say that it is. And so if we take the iris sepal length data as a population, we can then start to develop a sampling distribution if we sample randomly from this population. Since we know that this is a full population, we can calculate the parameter, right? So let's say, what is the population mean of sepal length? Well, it would be mean SL. And so that equals 5.84. Let's call it top mean, and that's mean SL. But what if we can't sample all 150 individuals in our population? Well, what we can do is we can sample from this population multiple times. And if we do it enough times, we can generate what's called a sampling distribution. And the way that we do that is, first we need an empty vector. Let's call it the estimated mean. And we just want to make it NA, or blank. Now, we need to use a special function called a for loop, or FOR. And a for loop is basically a function that runs a particular test or a particular analysis multiple times. And it is a loop, so it goes through the whole process and then it loops back on itself. It goes through the whole process and then loops back on itself. And we designate the number of loops by putting in parentheses after the for, I in 1 to, let's say we want to loop it 1,000 times. And so what this means is that it's going to loop 1,000 times, and it's going to start with the number 1. Now, in these curly brackets, we need to start putting our functions, the things we actually want to run 1,000 times. And let's say we want to sample 20 individuals from our population 1,000 times. And the way we do that is, let's make a vector x, and we use the function sample, because we're sampling from our population. And so where are we sampling from? We're sampling from SL. And then we need to tell it how many times to sample, and that is size, or sample size, and we're going to do it 20 times. And then it asks us if we want to replace. So this means that once we collect individual, do we want to put it back in so that we could potentially collect it again? And of course, we don't want to do that. So replace equals F, or replace equals false. The next thing we need to do is take that x, which is now a sample of 20 individuals, or 20 observations from that set of 150, we need to take the average of it. And so, of course, that is called the EST which we've already produced up above. And we need to take the mean of x. And this will give us our mean estimated from our 20 samples. One thing to note is that if you leave it as estimated.mean on its own, every time this loop goes through, it will overwrite itself. And we don't want to do that. We want estimated mean to be 1,000 observations long because we are sampling 1,000 times. So what we do is we use this I, which we've already designated above, and put it in square brackets. And there we go. So basically what this function will do is for 1 to 1,000 loops, it will take a random sample of 20 individuals from the population without replacement, and then take the mean of the sample, and then place it in the ith position, where I is the number of the loop. And so loop 1 will be I equals 1. Loop 500 will be I of 500. And so if we go ahead and run this whole thing, and the length of est mean, it is 1,000. So we're good. There's 1,000 observations. If we take a look at it, there's a lot of observations. What we can do is we can run another histogram, and instead of the histogram of the population, we can run the histogram of the samples, or the estimated means. And so, what we can see here on the x-axis is the estimated mean, so ranging less than 5.4 up to 6.4, frequency 0 to 200 here on the y-axis, and we can see that the middle bar is somewhere between 5.8 and 5.9. We can add a line here that, and we want it to be a vertical line, or V, equals our population mean to see how close were we to estimating our population. And there it is, right in the center. We'll make that line a little bit thicker. LWD equals 3. And as you can see, from our 1,000 samples, we were pretty good at estimating the true population mean by taking 1,000 random samples. This range between the estimated mean and the sampling mean is called sampling error. And we can measure that, and we can calculate sampling error by calculating what's called standard error. So we can take one sample, so x equals sample SL, size equals 20, place equals false, and the estimated SD is the standard deviation of x. So here we're just looking at one of our samples, and we can then calculate standard error, which is SE dot SL, and so that's, there is no built-in function for standard error in R, so we have to calculate it manually. So standard error is the standard deviation divided by the square root of n, which in this case is 20. And SC.SL is 0.22. And so what this means is that from a sample of 20, based on our estimated standard deviation, our observations of the mean, which in this case, the estimated mean is mean x, which which is 5.93, our actual estimate is 5.93 plus or minus 0.22. We suspect that our actual population mean is around 5.93 plus or minus 0.22 or 0.226. And if we look back at our population mean, 5.84, 5.93 minus 5.84 is 0.09. And so, in fact, yes, our population parameter, our population mean, is in fact 5.93 plus or minus 0.226.